All right, today we are talking about conics, which most of you guys, I believe, told me you did not get to as a separate section in Honors Algebra 2. We did not. Okay, so conics. This has a fascinating history, and I'm going to do some of this with the projector and some on the board. Can you guys all see on the projection that what you're looking at is an upside-down cone, a right-side-up cone, and a plane are all in the picture? Can you see that?
Yeah. Is the plane going through the cones, or?
Well, the plane right now isn't doing a whole lot. It's, if I rotate it a bit, see how you can barely see the plane at all right now?
Yeah.
And I think I can even tilt it a little bit. Let's see. There you go. Now, you see how the plane is going right down alongside the edges of the cone?
Yeah.
All right, hold on to that picture for a minute. That's actually the second thing I want to talk about. I got out of order because of how I left this.
Wait, do I have to draw the picture?
No, I won't say I have to draw the picture yet, but yes. Here is the ancient Greeks studied something called the Apollonian Cone. Apollonian coming from Apollo, the god who drove the chariot, which was the sun, across the sky. Don't really need to know your classical mythology for this. They studied this cone because they were brilliant, which is what I mainly want you to appreciate today. They studied the intersection of this cone and a plane. And a real Apollonian cone in space, abstract, not a physical one floating, is thought of today as a cone on the two cones intersecting at their tips. And there are certain shapes which are formed, most obvious one being, well, let's see, what happens if a plane slices across, straight across the cone, perfectly perpendicular to the height of the cone?
Creates a smaller cone.
Creates a smaller cone, but flat end. What geometric shape is at the bottom? Circle. If it's a right cylindrical cone, that'll be a perfect circle at the bottom. If the cone, why did I put that back on since that's the one that's hard to get off? If the plane were to slice through at more of an angle, what sort of shape? Later that evening.
More like an oval.
What sort of shape do we get?
Oval.
You guys know the math name for a perfectly symmetrical oval?
No.
It's actually called an ellipse. I'll talk about that for a second. If you slice at a certain angle, what does that look like? Looks like a parabola, but honestly on this cone I'm never sure. There's two things. There's a parabola and a hyperbola. They have similarities, but they're not the same thing.
The piece fell out.
Yeah, I know. The dowel fell out. This is a cheap Apollonian cone. That looks a little more parabolic to me. But we'll talk about the difference between the two of them in a second. So the ancient Greeks figured out certain things about all of those shapes. Now, they also figured out a couple other things that are a little easier to see up here. If this plane is perfectly intersecting the tips, where the two tips of these two cones meet, what shape is that? I'm sorry, what shape is that? How would you describe the intersection between the plane and those tips? Well, it doesn't look perpendicular.
Oh, so not that. I think.
What do they intersect at?
0.
0, they make a, somebody said it,
1.
point. They're going to intersect at a point right there. And so your first conic is actually just a point.
Is the line going like that? Is it 2 squares or is it 1?
It's one plane, and that's a resolution issue with this software. That's supposed to be one straight plane. The way this software works,
That was so that you could see the center.
it's not intentional. It's a glitch. The way I have the software set right now, it changes the color based on the height. So the blues are at the bottom, the reds, yellows and greens in the middle, reds at the top, and that's just causing a resolution glitch in there. So we have a point right there. Now, that's your first conic actually, is just a point. Now I'm going to go back, and I want to try and get it right back along that edge. A little bit more. So that plane is now going As I say, infinite amount of points isn't wrong, but more specifically, it looks like, if I've lined it up correctly, as if this plane is barely touching, tangent in that Latin sense the word touch. In math means barely touching at one point, or in this case, along an infinite series of points. That looks to me like that intersection of this plane and these two cones will be a line. Can you guys see that? All right, so your second conic is actually just a straight line.
What's the actual definition of a conic?
We'll get to that in a second. I mean, it's the intersection of a plane and a cone, but it's so much more. Now let's see what else I can do with this. I have this set to do. Okay, now I'm moving my plane a bit, and
So
now
you're slicing it like with the.
yeah, now I'm slicing it. Actually, you know what? I did not want to do that yet. I'm going to slice it like one of the other shapes we just talked about. But first, I'm going to go back and rotate it some more. Now that's a resolution glitch where it's disappearing as it gets closer to vertical in the middle. I don't know how to fix that in this software. It's great software otherwise.
But it should be completely going down.
It should be completely going down, yeah. Now, I like how that line stayed up. If you picture this plane slicing right through the middle, okay? This may cause the plane to disappear completely if I go look at it straight. No, it's still there a little bit. Okay, if you picture that plane now as being completely vertical and cutting through both cones, cutting them exactly in half, then the intersection will still be a line here, but that plane will also create another line going down this side. So two intersecting lines is also a form of conic. And these three get a special name, and hopefully people can see what I write over here on the video, because I know it's darker because of the contrast. But these are called the degenerate conics.
Those three are
Just these three. Just these three are called the degenerate conics. There's 6 conics we're going to look at total today.
Are we going to get to what's a conic today? It's kind of bothering me.
Yep.
We're using conic.
And I use the word, and what is it?
Yeah.
Think of it as just the intersection of a point, of a plane and 2 cones like this for now. And there's only 6 real possibilities. And I'll break it down a little bit more. And I already gave away what some of the other ones are. But let's see. Let me rotate this back to a nice angle. And I think for this one, I'll go ahead and start with one that's not as familiar to you. So now I'm moving this plane out. Here we go.
What's happening in the middle?
There's a sphere in there.
Yeah.
That's going to take me, that you're going to have to be a little patient with. I think the sphere is part of what's throwing off the resolution. But,
Is it the computer or
no, I created the sphere in there. And I'll tell you why it's there in a second.
that has trouble with
Oh, I'm not sure if it's this computer or the software, to be honest. I haven't run this software or anything else in a while. Okay, now we get another color. Right here what I have is a vertical plane. It doesn't have to be vertical. It could be tilted slightly. But in this case, I have the plane. Maybe a dead-on shot will be clearer. Since I moved the plane out away from the center a little bit, can you guys see that its point of intersection is now along this shape? Okay? And can you see up here, it's along a symmetrical path up there
Yeah.
before the plane disappears.
Or should we draw a
Well,
line?
that one's
So,
the
That's a
top.
great
looks
question.
like there's a sphere. And
Yeah, there's a sphere in there, and that's a little bit,
bottom
there's
is,
there's no sphere visible on the bottom right now.
Right now.
Yeah, well, it's, I can bring it in, but that's a little bit, that's something I put in the software for a different reason. But
it just looks like it's a sphere.
like a spherical parabola, interesting. What you're seeing is the cone coming out, giving it that 3D effect. But remember, all we're talking about is where the plane hits the cone. So it does kind of look like that. But we're only talking about this one-dimensional path right here, right along the intersection. It's actually two-dimensional, I'm sorry. We're drawing this, it's a one-dimensional path, but we're looking at a two-dimensional shape here and here. Do you have to draw those lines, Remy asked? Soon, yes. What you get here,
Just draw this freaking, thing. Time.
not each time, I'll give you pictures of these later.
Okay.
I'll give you a graph. If you can draw it, it'd be good, if that'll help you remember it.
Right.
If you can't draw it and pay attention, don't worry about it. This is actually called a hyperbola. You've seen a version of this before, and I'll tell you where soon, but not today. A hyperbola has two wings, and they look kind of like parabolas, and some people draw them quickly like parabolas. They are not parabolas at all. And in fact, if you take a parabola and a hyperbola, you could, on transparent pieces of paper, you could never superimpose them over one another. Their shapes are actually very, very different. A hyperbola, Remy, you asked about these two lines that I left up there that represent where the plane was slicing through the middle. The hyperbola has asymptotes. The hyperbola, remember what an asymptote is?
Yeah, it's fine, it
Can't go, well, that's actually winds up not being true later as well. It's a line you keep getting closer and closer to. You probably learned it before, it's a line getting closer and closer into, but never reaching.
Yeah.
End of this year, we'll talk about limits, and we'll talk about sort of what happens when you,
Reach it.
well, think about reaching it. It's a little different, we'll get to that. But the hyperbola, Remy, will have an asymptote relationship with these lines. So when we get to graphing hyperbolas, you will be graphing the asymptotes as well. Okay? But a hyperbola is created by the plane slicing through both cones. It doesn't have to be perfectly vertical, the plane. You can tilt the plane, and you'll get a slightly different shape to your hyperbola, as long as it hits both cones. Does that make sense? Okay? And it does follow asymptotes. That's different from any of the other shapes we're going to talk about. These lines won't be helpful on the next thing I show you. So let me get rid of them.
Can a conic be with different shapes?
It can only be in the families of shapes I'm showing you right now.
So it can't be like a square and a
No.
rectangle?
Nope, it's only what you can imagine the plane creating with the cones. Now for this next one, I don't want to do that. I want to rotate my plane. That's about where I want. Maybe a tiny bit more. That's good. And I want to bring my plane a little closer to the center. That's the wrong direction. Ignore the sphere in the middle for now. Okay, this is a fun one.
Is it perpendicular to the bottom cone?
Is it perpendicular to the bottom cone? Perpendicular is not quite the word. Oh, perpendicular.
Very close.
Not quite perpendicular. It's what I'm going for is very close to parallel here and here. And at that angle, it certainly doesn't look it, but very close. If I can get it, I'd like to get it. I'd like to be using the right scroll bar. Okay. Let's see if I can get it. Does that plane look parallel to the edge of that cone now?
No, wait.
To the edge of the cone? Yeah. No.
To this edge along here.
Yeah.
Yeah.
Just a little more.
A little more? Danny, you're being very picky here.
There.
That looks like a little better. It's hard to tell with perspective. Okay. Can you guys see this is being the intersection between that plane and that cone?
Wait, where? Yeah.
That's where that plane hits that cone.
Can you turn it like so we can see it from the side?
Well, that'll ruin my drawing, but
Uh,
be more like that. Oh, how's that looking into it there?
That's better.
Can you see the intersection a little better there?
I like it better the other one. But okay, this one.
Let's see what I can do with that. Let me erase my drawing because now that's distracting, and I'll use a different color. So I see something, ignore that sphere, I see something going kind of like that.
No, I see.
Yeah, I see it.
Okay? If you get the plane so that it's perfectly parallel to that edge of that other cone, I've got the plane going through the top cone, and I'm keeping it parallel to the edge of that bottom cone. If it's parallel to the edge of that bottom cone, will it ever hit that bottom cone? No, so all I get is this shape through the top cone. What does that look like? Smiley face. What kind of shape have you seen like that before in Algebra 1 and Algebra 2? Keeps going up forever.
Parabola.
Through parabola. Keeps going up forever through the top cone. It doesn't get a bottom half. Because again,
That's not.
well, not really. It's very useful as it is. Because again, it only goes through. I think at this angle I can see it a little more clearly actually. I see the parabola up here. It's a very tilted view of one. And as long as this is truly parallel to this edge, it will never hit this edge. So that's why a parabola does not have a second half. But that's what a parabola actually is. Parabola is the intersection of a plane and a cone in such a way that the plane is parallel to the further edge of the cone it's slicing through, and if you have this two-cone setup, it's parallel to the closer edge of the cone it never touches. That's one of the definitions of a parabola or of a conic. Diego, one reason I'm hesitating is we're going to define a conic literally 4 or 5 different ways over the next month. All right? Now there's one more of these I need to talk about.
We're going to spend a month on Conics?
Between this and maybe a little less than that, between this and polar forms. We'll come back to them a few times. And we're going to rotate them. We're going to do all sorts of crazy things with them.
Robbie, you're gonna live, sleep.
All right. Anyway, now I'm rotating this a little bit more. Okay, what's the shape? Let me erase my distracting drawing. But what shape are we going to get of that plane slicing across one cone? Ellipse. You can see parts of it in there.
Yeah.
If I try and get it so that it's...
Yeah, we can see it there.
All right. This side seems pretty easy to see.
The box shows a stripe in there.
Yeah.
What's the box doing?
I'll tell you that, possibly in a few minutes at the end. That's not a great ellipse. That is an ellipse, though. That's the last type of conic. But there is a special type of ellipse. A very special type of ellipse.
Can any of these, like a parabola, or maybe on the bottom cone instead of the top cone?
Absolutely. They can be through either cone. What do you think happens when you make the plane perfectly perpendicular to the height of the cone?
A circle.
You get a circle. Very good. And the software is struggling to let me show you that. There we go. I'm struggling to help the software do it. So that,
I'm sure that's the weird circle.
it looks concentric from here. The one that's at the intersection of the plane,
Looks like there's 3.
yeah. Well, that's the sphere on the inside as well.
Yeah.
I'll tell you why that's there in a sec. That's the one that shows, that's the plane intersecting with the cone. And the circle is just a special case of the ellipse.
It's not a different type of cone.
No, it doesn't get its own. It's not its own family. It's just the. It's an ellipse with a couple of special properties we'll talk about. So if you're looking at a plane and a cone or a plane and two cones, you can make a point, a single line. You can make a point, a single line, or two intersecting lines. But slightly more interesting from my perspective, you can also make an ellipse. You can make a parabola. These are what we'll spend the most time on. And you can make a hyperbola.
I was going to put them like all the way at the edge. Like the two cones like perpendicular of the plane.
Oh, right through the middle?
No, like that, but on that side.
What if you add a second plane?
Oh, don't get me started on that. I'm still not sure what you're asking, Diego. Where does the plane to go?
You know, like if you put the plane going down like that.
Oh, you just get a different hyperbola.
Why?
if it's up and down, like if it's still hitting both of them, and I move it, that would be the radius of the sphere inside.
Can't you in a second?
I could, not quickly with this software. So I just get a different shape to the hyperbola. This actually between
But if it
two.
was like perpendicular or something touching.
It was perfectly straight.
Yeah.
Well, remember the cones go on forever.
Oh, that's right.
So if the cones go on forever and the plane goes on forever, that actually allows you to get any size or shape, parabola or hyperbola or. Plus, you can also change. Another thing that you can change to get every shape is one thing that's not set in stone is, take a look at this gentleman. What am I doing to the cones now?
Ooh, what?
Opening them,
I'm making the cones more open, more wide. And what else can I do to the cones?
making them smaller.
Right, so if I make these cones really skinny, and let me bring that, now they do go on forever, so they still hit that plane. And then I start bringing the plane back in, you can get a very skinny hyperbola or parabola that way. Look at this, this one will actually be a hyperbola, but look at how much more narrow that hyperbola would be
Yeah.
in that case. It would get much more skinny. And if I made this perpendicular, the cone, my intersecting lines would both have a much steeper slope, one negative, one positive. Does that make sense?
Yep.
Okay, you guys got a visual for that now. Okay, so I'm going to turn off the projector and do a little bit on the board. We may come back to the projector if you have questions. Any questions on what I've done on the board so far? One yes, no?
Are we gonna get to the purpose of why we use it?
Oh, yes. Okay, now,
Like, is it actually useful in real life?
you don't even know. Okay,
Well, clearly, because he's asking.
here's the deal with conics in general. The ancient Greeks figured out that this was everything you could get by changing the orientation of a plane that intersects these two cones, or by changing how narrowly or widely the cones open. They also figured out a couple of other things, and we'll start with these three, the hyperbola, the parabola, and the ellipse. I'm going to start with the parabola. Okay, that's probably the most fun. I'll also definitely get to the ellipse. I may not get to the hyperbola today. Each conic has what is called a locus. And a locus is,
Didn't we do this in geometry?
yes.
Okay.
So, yes, but let me make sure help me make it clear to everyone else. Yeah, we talked about this. A locus is a rule. And every one of these follows a rule. In addition to that, they have some properties.
It's like crazy.
The locus, it's loco, right? Okay, the locus of a parabola. The rule of a parabola is not y equals x squared. We'll talk about where that came from later. The locus of a parabola, the actual rule is, it is the set of all points equally distant from a point, and that point is called the focus.
Focus and locus.
The focus of the locus, yeah, you're not wrong. From a point and a line. And that line is called a directrix. A parabola is actually the set of all points that are the exact same distance from some point and some line. Okay? So if I draw that line, I'm going to label with a lowercase d for directrix. And I draw some point out here, which I'll call capital F for focus. The parabola is all the points that are the same distance from both. Now, distance from a line we usually mean perpendicular. I'm going to draw this focus in closer, because I just realized it's going to be limiting if I don't. So let's start with something that's sort of obvious, I hope. Here's a line from the focus to the directrix. It's perpendicular to the directrix. Here is a point right in the middle of that line. That segment. If it's in the middle of this segment, is it the same distance from the focus as it is from the directrix? If it's halfway between the two, is it right in the middle?
Yeah.
Yes, it is. That's actually where your vertex is always going to be on your parabola.
Middle?
Right between the focus and the
Or
directrix. Now, if I go over here and I pick some point, and I make sure that that point is, remember this from geometry, where you draw the lines and you put the little line through them to show they're congruent.
oh yeah.
If those two segments are congruent, connecting the segment connecting the point to the directrix and the point to the focus, then that point is on the parabola because it obeys the rule.
The top lines, the y.
Forget about the axis. There are no x and y axes. That wasn't invented until 1637 by René Descartes. We're back in Euclid's time now. No such thing. Now, there has to be some point. If I keep going in this direction, straight parallel to the directrix, at some point, I'm going to be as far from the focus as I am from the directrix. Does that make sense? If I start walking away from this focal point, at some point I'll have walked the distance that is exactly, and I'll be just as far from the focus as I am from the directrix.
Is that a square? Maybe it's a square.
Yes, that'll create a square. It's not a very well drawn square.
But it's supposed to be as river.
Yes. And I can do that in both directions. I can walk up here until I'm the same distance from both the focus and the directrix. And those are all points on my parabola. And my parabola doesn't have to go up or down. It doesn't have to go left or right. It can go at any angle you want. The genius of René Descartes in 1637 inventing algebra, he didn't invent algebra just to make classes harder for you guys. If he hadn't figured out that this could also be described by y equals x squared, you would still be graphing these this way. You wouldn't have to not learn them. Did you guys ever in geometry do a unit where you had that compass and a ruler and you made circles and tried to figure midpoints?
Yeah.
Okay, that's how you would be drawing this. Y equals x squared is actually a huge improvement.
So he's a friend now, right?
He's, yeah, given that you had to learn parabolas anyway, he's very much your friend. That's the locus of your parabola. That's what it really means. Why do we care about this? What do parabolas tell us? May I erase this part?
Squares,
Yeah.
quadratics.
Quadratics. You guys notice what we use quadratics a lot for in physics? Maybe
Velocity.
every falling object? Accelerations, not so much as velocity. Everything that accelerates behaves quadratically. The ancient Greeks knew that this described the motion of a falling object. I'll come back to that in a second. Not only that, parabolas have another interesting quality. That's the impressive part. I mean, the tools they used to figure this out were basically sticks and mud. You know, they're making to write and they were doing it mostly in
Can
prose.
you cut it in half and it'll be exact same as
It is symmetrical, yes. My drawings don't do a good job of showing. Turns out, if you have a flat a parabolic object of any sort, let's say you built a pool table in the shape of the end of a, and one end was in the shape of a parabola. Turns out that anything, well, actually let's go back to Nate, you just said they're symmetrical, right?
Yep.
That's my axis of symmetry, remember that term?
Yeah.
Okay, turns out anything that enters a parabola parallel to the axis of symmetry will always bounce off the parabola straight at the focal point.
Yeah, look ahead like.
Hold that thought. We went over that before. It also, you've heard that before, no fair. But good memory. It also turns out that anything that leaves the focal point, no matter in what direction it leaves, if it hits the side of the parabola,
Wait, so is each side of the parabola supposed to be equal?
it's supposed to be, yeah.
And the line is supposed to be perpendicular, or?
The line is supposed to be straight down the middle.
So
I apologize for the
So
quality
it's
of my
supposed to
drawing.
be in a slant if it's.
Yes, this is supposed to be a slanted parabola. Now, Anything that really goes away from the focus and hits the side of the parabola goes out perfectly parallel to the axis of symmetry. What Nate's remembering is actually that this is the modern design of a car headlight. If you're building a car headlight, you find a reflective surface. You make a three-dimensional parabola called a paraboloid. It doesn't go on forever, you cut it off at some point. You put the bulb right at the focus of your paraboloid, which is just a 3D parabola. The light then leaves, I'll get rid of the one going this way. The light then leaves the bulb in all directions. Everywhere the beam of light hits the parabola, it goes out perfectly perpendicular to the axis of symmetry. If it goes out, if this is the end of your car headlight, some of the light goes out and doesn't hit it at all.
Couldn't you do that in reverse and
So it's like a backlight.
like start a
Invent a satellite dish?
No,
Yes.
no, like have a combustion.
Hold that thought. Don't go there now. We don't have time. All flashlights. Any well-built flashlight has this property. Which is why if you ever notice when you're looking at car headlights, you'll see a thin amount of light going out like that, but you'll see a really thicker, more concentrated one coming straight out. The thicker concentrated beam in the middle is from all the light, counterintuitively, that does not come right at you. It's from all the light that goes back here and bounces out. Did the ancient Greeks really understand this? Well, Mythbusters has been all over Archimedes' design of a solar laser.
But he drew.
They think he might have built one, actually. He was using like wicker and bamboo, or whatever the equivalent of bamboo is. Greece, I don't think it grows there, but and he built a basket in the shape of a parabola, filled it with reflective surfaces, the best mirrors he could find, and he figured out that on a sunny day, he could focus the sunlight. The sunlight would all come in, would all go out through the focus, and if you build a really, really, really wide parabola, the focus can be a mile away. And his idea was all the sunlight would come in from all directions and all be focused at that focal point.
So they would all bounce back to the sun?
No, they would bounce,
Basically.
the sunlights could you use to set fire to the sail of an enemy ship or something, was his idea.
It's actually really cool.
Mythbusters and college campuses all over the country have tried to build these things. Some of them have successfully set fire to things. It really depends on how sunny it is. I believe most of the ones that have worked have used better mirrors than Archimedes could possibly have gotten a hold of in his life. So he probably couldn't have built it.
Well, isn't that, if you take like a
So,
movie
yeah,
and
it's
reflect the sun to something, like when
Yeah.
you do that and they hit it to your eye, like light stage?
You can do, yes, he didn't have mirrors that good.
Yeah, but isn't that kind of the same property when you take a mirror?
Hold that thought, you're getting ahead of yourself. There's no quick way to learn this yet. I know you're impatient.
Couldn't you technically do it to fix it with sand?
Not right now. All right, we'll get to that. Not yet. That is a property of parabolas, though, that the ancient Greeks understood. Stop. Ellipse. Okay. The property of an ellipse is a little bit more complicated. The locus of an ellipse. An ellipse is all the points such that the sums of their distances from two foci, plural of focus, sum singular, sorry, such that the sum of their distances from two foci is a constant. Now in English that's a little hard to follow, but the sum of their distances from two foci is a constant. Sum is the noun, singular is the verb. I think I'm on good grammatical ground here. So an ellipse has two foci. Focus 1, focus 2. What that means is, from this focus, you get a distance. I'll call that distance 2.
Is that that's an ellipse, right? Not a circle.
Correct, this is an ellipse. From that same point, we have a distance to focus 1. distance 1 plus distance 2 is the same constant number for each ellipse. That's their definition. Ellipses also have an interesting physical property. Anything that passes through focus 2 and bounces off the side of the ellipse will always pass through focus 1. I won't have time for any questions on this. We just have time to tell you about it. 2 more things. But someone built an elliptical pool table once. Pool table in perfect shape of an ellipse, excuse me, with a pocket at one of the foci and a little dot there. And if you shoot the pool ball at any angle and it crosses that dot, it will bounce back and go through that pocket.
Wait.
As long as you hit it straight and the table's level and all that, there's nothing weird going on like that.
Is friction involved?
Well, if you don't hit it hard enough, friction will stop it. And spin is also involved, which makes it more complicated. But a good clean shot that isn't wobbling because of spin and is hard enough to overcome the friction and everything else. If it passes through this focus, it'll then pass through that focus after it bounces.
So if you take a ball, put it in the dot, and just hit it anywhere?
As long as yeah.
Wow.
And if it's not on the dot, just make sure you hit it so it crosses over the dot.
But if it's on the dot, it'll still work?
Yeah, as long as you hit it clean and it doesn't get any weird spin. Sound waves follow this principle. Ancient spying technique. Let's make a hypothetical. It's the Soviet Union, and it's in a Cold War with the United States, and there's a restaurant where the United States has checked and found out there are no electronic bugging devices. So Americans figure that's a safe place to talk about secrets. So the Americans are led to a special VIP table here. And there's a little Russian guy doing a crossword puzzle over here. Everything the Americans say, all their sound waves, are going to radiate out from their mouths. They're going to bounce off the wall. And they'll all bounce through that focus. Which means no matter how quietly they talk, no matter how much other noise there is in the room, especially if the ceiling is also elliptical, someone sitting here can hear everything said here. No electronic amplification necessary, no matter how much noise is in the middle. So that little Russian guy doing the software puzzle is probably writing down every kind of word said at this table.
Software puzzle.
Yeah, soft. Crossword puzzle, wow. There's a room like this down at the Capitol. There's in the veranda, I think, there are 2 places you can stand. You can see this in
I
action.
heard about that.
Yeah.
Yeah. Say something. There's a right across the room over here.
Give you one more use for an ellipse. And if the bell rings, hang on for one more second. I just have one more thing to say. If these 2 foci are different air bases, let's say they're different helicopter bases. Here's one helicopter base, here's another helicopter base. And you have a fuel that lets you go a certain range, right? If you're going to fly in a straight line to a destination, and then fly in a straight line to the other base, you have to start here, wind up here, and you're only flying straight lines. This ellipse perfectly describes the range of places you can go. Because the rule is, the sum of the distances is a constant. The distance from here to there, plus the distance from that same point to there, is some number. So if you have a limited range, if you can fly 300 miles in your helicopter, you can fly anywhere where you go somewhere, stop, and then go back where it adds up to 300, right? Anywhere you go on the ellipse, if I go from here to here and then back, these 2 distances will add up to that range. If I go from here to here and back, these 2 distances will stay in that range. So if you want to start here and end here, and you've got a mission to do, how do you know if you can pull it off? Is it inside this ellipse? Because if you're going in a straight line, this is the furthest you can fly from this focus and make it to that focus. If you go outside, if you step outside that ellipse, you will not have the fuel to get back to that one.
How do you find the
Why?
focus 2 ellipse?
How do you find the what?
The focus 2 foci.
Well, they would be the positions of, what would you do is you'd say this is 1 base, this is 2 base, and you would just draw on a coordinate plane.
I'm not saying like specifically not example, I'm saying they give you like...
Hold that thought. We're going to get to that with the algebra. We're going to spend weeks answering your questions. It's going to be frustrating. Last thing I will say about these shapes is one other thing the ancient Greeks figured out from dropping objects and watching the heavens and a couple of other things. Every single object in the universe, every object in the universe that cannot fly under its own power, that is in the air or in space and cannot fly under its own power, does not have a rocket ship attached to it, does not have a jetpack, is not Superman or a bird.
Oh, it's a parabola.
If it's sitting still, it's a point. It's sitting at a point. If it's moving through space away from any gravitational field, it'll move in a straight line. We talked about that in physics, right? If there are no other forces involved, and it'll bounce off something in a symmetrical way, just like those two intersecting lines of the cone. If it's falling on Earth, it's falling in a pattern best described by a parabola, or if it's tossed in the air, it will always follow a parabolic path. If it is an orbit, it is actually in an elliptical orbit, rarely a circular one, the Earth around the Sun, the Moon around the Earth. And some things also will follow a hyperbolic path, which means the three degenerate conics and the three other conics describe the motion of any object that is in the air and cannot fly under its own power anywhere in the universe.
Is there any?
There's a reason for that.
Is there any orbit that's like circular?
Unless there's negative.
I think so, but I'm not 100% sure actually if they're not all ellipticals. We'll talk about the difference between ellipses and that. We'll get into the math behind this starting tomorrow, but I will refer back to locuses and foci and the rules behind circles and ellipses and the rest of these throughout the next week or two, so you need to know all this.
Homework is to contemplate.
Homework is to understand everything I said today.
Good luck with that.